So let's now think about the controllability of a system. What does that mean? Well, if we've got a state space system, x dot equals x plus bu, the system is controllable if we can find an input u that gets the system into any state. Here we're actually not going to consider the output measurements and only focus on the state evolution. Okay. So the idea is, can we have a system which we can get from any input state to any other state just by the input factor u. Now, if we've written our system matrix A diagonally, it's relatively easy to see what's going on. And basically what this means is, if we've written x dot equals A, where this is diagonal, times x plus b times u, it means in this particular state, in this case, if we have a diagonal A matrix, it means the system is completely decoupled. There's no mixing across the states. So what happens in state 1 stays in state 1, basically. So in this particular example, we can write down what the individual components of x dot are as follows. We can say x dot 1 equals lambda 1 times x1 plus b1 times u. X dot 2 equals lambda 2 times x2 plus b2u. And x dot 3 equals lambda 3 x3 plus b3u. And what you can see in this particular case is that we can actually affect all of the states by the input u, right? So because we can affect all of the states, because we're affecting all what's going to happen, the evolution in the x dot vectors, we can say that the system is controllable. Let's think of another example where that's not the case. Again, let's think about an uncoupled system where we have a diagonal A matrix, and in this case what we have is a B vector which is actually got a 0 element in it. So we could write down one more time in this case what the x dots terms look like, and again we can see we have x dot 1 is lambda 1 x1, this times the first element in the x vector, plus b1u. X dot 2 equals lambda 2 times its corresponding element plus b2u. But x dot 3 is only a function of the state x3. It's not a function of the input. Therefore, the input cannot affect x3, cannot affect x dot 3, and it therefore cannot affect x3. So in this case, the controller input cannot influence all of the state variables. It can't affect x3. Therefore, the system is not controllable. So, now normally the A matrix is not going to be diagonal, and we can have couplings in there as well. So we can't just look at the equations in that way or by inspection and say whether or not things are going to be okay or not. In which case we have to do something which basically means we have to calculate the controllability matrix. And the controllability matrix is given by the following expression. Controllability matrix equals an expression built up from B concatenated with A times B concatenated with A squared B and so on up to A n minus 1 times B. So basically, depending on the rank, we have a different number of these terms in here. If we had a second order system, we just have B and AB in here. So let's do an example of this. So let's have a look at this system. X dot equals this A matrix times the state plus this B matrix times U. And we have an output relation as well. So we have the A matrix and the B matrix. We need to calculate the controllability matrix, which is B concatenated with A and B. So we know what B is already, right? We've already got that 2, 1. Now we've got to calculate what A times B is. So A times B, A matrix times B matrix. And you can see this is minus 2 times 2, that's minus 4, plus 0. 0 times 2, minus 1 times 1, that's minus 1. Okay. So substituting in B and AB, we end up with the controllability matrix 2 minus 4, 1 minus 1. Now, in order to tell whether or not that is full rank, and it has to be full rank for this system to be controllable, we need to see whether or not we can get that into echelon form. And basically echelon form means upper triangular form, in such a way that we end up with a matrix which doesn't have a complete row that is 0. So in order to do that, what we can do, we can basically subtract rows from each other. That's perfectly legitimate to do in order to try to get things into this echelon form. So in order to do that, what we'd say is we're going to consider row 2. We want basically we want to get a 0 here, and then it'll have an upper triangular matrix here. So this has got to be reduced to 0. So what we're going to do is we're going to say row 2 times row 2 is going to be made of 2 times the current row 2, take away row 1, because we're allowed to do that. We're basically looking for linear dependencies. So it's going to be 2 times 1, take away 2, that goes to 0, and then 2 times minus 1, that's minus 2, take away minus 4. And that's going to give us, well, obviously the first row stays the same. This goes to 0, this goes to 2. But you can see that this is now reduced echelon form, and there is no row that is completely 0. Therefore, the matrix has got rank 2. So it's got rank 2, it's a 2 by 2 matrix, so it's full rank, therefore the system is controllable. So just say we didn't work through from first principles how this controllability matrix comes about, but we haven't really got time in this module to do that. That would be something for a more advanced control engineering course. Just like looking at controllability, the other thing we need to look at is observability, right? So what does that mean? Well, again, we look at our state space equations, x dot equals ax plus bu, y equals cx plus du. A system is observable, basically, if we can know all of its states. If we can look at the output and we can say, yes, we can work out what the states are. Now, in many applications, you can't necessarily do that anyway, and we'd have to use an observer, right? So, and that's something else we'll come to a little bit later on. So let's think about a simple example again in terms of using diagonal A matrix form and see what the system would look like. In this case, we have a matrix A dot equals A times x plus B times U, and y equals the C matrix times x. Again, because the matrix is diagonal, it means state 1 only affects state 1, state 2 only affects state 2, and state 3 only affects state 3. So it's not going to be coupled together. If it was coupled, we can't just look at these things and come up with these equations. So in this particular equation, what we see now is, and now we care actually about the output as well, because we want to basically know from the output whether or not we can have an effect on the state. See the states. We see the output y equals c1 times x1 plus c2 times x2 plus c3 times x3. So x is here actually a vector. So as you can see in this particular case, all the state variables are coupled to the output, right? So they all have an effect on the output. Therefore, the system's observable. However, what happens if we have this system and we don't have an output vector which is affected by all of the states? In this case, we have a more limited value relationship for the output. So y is now c1x1 plus c2x2. In this case, the states are not all coupled to the output. In fact, x3 has got no effect on the output. So there's no way, right, we can ever find out what x3 is up to. So it's not going to be observable. Once again, in general, A will not be diagonal. So we've got to use something called the observability matrix. Again, we're not going to go through the derivation of this, but we're just going to quote the result. So the observability matrix is concatenated in a vertical sense, and it basically consists of C, CA, and CA n minus 1 to the power CA n minus 1. So if we had a 2 by 2 matrix, we just have the first two terms. So let's just do that. So given we've got our system again, in this case we care actually about the C. So we've got our A and we've got our C. Let's calculate, well, we know what the C is. We need to calculate CA, right? So C times A, so it's rows by columns. So it's 3 times minus 2 plus 0, that's minus 6. 3 times 0 is 0. 0 times minus 1 is 0. So we end up with a minus 6, 0. So we need to concatenate vertically these two things together. Now I can immediately look at that and I can tell you that this thing is not going to be full rank, because if there's any linear dependency, right, between rows, we know it's basically the same equation, it's just it's scaled differently. So we try doing echelon Gaussian elimination to get echelon form. What you're going to find is the whole line's going to disappear. So let's say we want to get rid of this and turn this into a 0. So what we can do is we can add on 2 lots, right? Row 2 goes to row 2 plus 2 lots of row 1. So we multiply the top one by 2. It's going to be minus 6 plus 6, and that's going to go to 0. And then we've got 2 lots of 0 plus 0, that's still going to be 0. So we're going to end up with an equation, a matrix which looks like this, 3, 0, 0, 0. But now we see we've got zeros in one of the row. That means that this matrix is not full rank. It means basically that these two were linearly dependent, and they are. It's just a factor of minus 2 between them, right? So we see immediately then in this case the system is not observable, right? So just the important results that we're going to worry about when we're doing analysis on this particular module. It'd be more interesting, exciting stuff if you were taking it further, but these are the main things. We need to find eigenvalues. They've got to satisfy the equation ax equals lambda x. The non-trivial solution is when we find the determinant of the matrix, there's a lambda missing there, A minus lambda I. If we have a 2 by 2 matrix, the controllability matrix is given by B, A, B. And if we've got a 2 by 2 system, the observability matrix is given by C, C, A.